Good evening, Manchester.
Good evening.
This is Warping Space and Time, the science fact and a little bit of the science fiction of black holes. So I'll be giving you a very brief history, sort of 1 minute brief history. Then we'll be spending most of the time looking at a few science facts, and then we'll be briefly looking at science fiction before wrapping up at the end there. So let's just deal with the definition. I guess you're probably familiar with the definition, but let's just make sure that we're all on the same page. A black hole is not an object as such. It's a region of space from which nothing, i.e. not even light, can escape. And if you think about the concept of a black hole, when did this idea first arise? A lot of people assume it was in the 1950s or 60s when it was very popular to think about the nature of black holes. But actually, the origin of black holes goes back rather earlier, to 1783, when the Reverend John Mitchell, if you'll excuse me paraphrasing directly from his quote there, if a sphere of the same density of the sun were to exceed that of the sun in the proportion 500 to 1, then all light emitted from such a body would be made to return by its gravity. In other words, if we take something like the sun and just scale it up and keep the same density, eventually it's so massive its gravity will be strong enough not to allow light to escape. So that's been known for a long, long time. But that was essentially forgotten in the 1800s. Everybody just forgot this particular quote from the Reverend John Mitchell. And the idea of this concept of a dark star was basically ditched completely. It resurrected itself in the early 1900s. I'm not going to go through all this detail, but this is there in the slides and handouts of the slides if you're interested, just to remind you that there are quite a few key players in the early 1900s that are dedicated to the idea of space and time that are so warped by the existence of what we now call black holes. That term was only coined later in the century. But basically, these players have taken Einstein's equations from general relativity and asked themselves what would happen if we took a lot of mass and condensed it into a small volume. And in particular, it was realized that odd things happen if you take a mass and compress it into a sphere of a particular radius, and this has become known as the Schwarzschild radius. Odd things start to happen. And it was also realized by lots of people that stars might collapse under their own gravity to form these objects. And it was also realized that not only space does odd things, it was also realized that when you apply Einstein's general relativity to extremely compact, i.e. large mass in a small volume objects, you also get these odd effects such as time standing still. So you might call them black holes, you might call them dark stars. For a little while, they were also called frozen stars because time stands still at the event horizon. But we're not going to go into all of those details of how they came to these conclusions. Those names are there for you to go and chase if you so wish afterwards. I'm going to be describing 4 parts of the puzzle here for black holes. Firstly, we have to understand what we mean by escape velocity, because that's key to an understanding of a black hole when the escape velocity reaches the speed of light. We need to have not really a deep understanding of general relativity, but I'm just going to touch on it because that again is key, because all of the concepts of black holes have come out of Einstein's general relativity. We'll then have a think about how stars might form black holes and the fact that there seem to be black holes at the centers of galaxies. So we'll have a little think about stellar evolution. And then we'll ask ourselves, how do we actually go about detecting these things? How do we detect gravity at a distance? So I'm going to be looking at each of those 4 pieces of the puzzle. In principle, it doesn't really matter which order we take these 4 pieces in, but I'm going to cover them in the order I've just indicated. And in this particular case, because we've got pieces of the jigsaw, I'm going to put the colored piece of the jigsaw up in the top left there, so to remind you which particular thing we're dealing with as we go through these 4 pieces. And the same goes for the handouts. If you look at the handout, the top left corner will remind you which particular piece of the puzzle we're thinking about. So we're going to start with escape velocity. The escape velocity of a surface of a body, if we just consider spherical astronomical objects, or in principle spherical objects of any kind. Physicists just prefer a sphere because it's easier to deal with than any other complex shape. If you want to work out how fast do I have to throw something for that object to leave, it doesn't actually matter which direction you throw it. If I wanted this to escape the Earth's pull, ignoring the effects of ignoring the effects of atmospheric friction, it doesn't actually matter if I throw this directly up, or I throw it at 45 degrees, or I throw it horizontally. The escape velocity is still the same. And the escape velocity depends only on that ratio of the mass to the distance to the center of the object we're dealing with. If we're standing on the surface of an object, then the distance from us to the center is just the radius. So I've written it there as mass divided by radius. If we were at some other distance, then we would just put distance in there rather than the value of r. But the point is, it only depends on that ratio. Mass divided by the radius is the only thing that determines the escape velocity. If we put some numbers in, again, we're not going to go through the maths, but if we were to do this and actually calculate how fast you have to throw something to get it to escape, the escape velocity from the surface of the moon is about 2 kilometers per second, or in old money, for those that prefer it, 5,000 miles an hour. If we scale up to the Earth, Earth is larger, so we're further away from the center, but it's much more massive by a couple of orders of magnitude. So it turns out the escape velocity from the Earth is about 11 kilometers per second, 25,000 miles an hour. That's about the speed that the Apollo astronauts had to go in order to escape Earth and get to the moon. If we go to the sun, again, larger, so r is larger, but mass is very much larger rather than just the r being a little bit larger. Mass is very much larger, so the mass dominates. And so with the sun, if you were to stand on the surface of the sun, not recommended, then the escape velocity would be a whopping 600 kilometers per second, or more than 1,000,000 miles an hour, which sounds ludicrously fast until you remember that it's only a tiny, tiny fraction of the speed of light, which is just as well, because we know, of course, that light does leave the surface of the sun and arrive at Earth, and no surprise that it is the escape velocity is less than the speed of light. It's perhaps a surprise it is so small it's not even 1% of the speed of light. So the sun is a long, long, long way from holding on to the light that it's emitting. What happens, let's just do a thought experiment. What if we take the mass of the sun? We know that the escape velocity depends on mass divided by radius. Why don't we just take the mass of the sun and simply compress it to a denser and denser object, make it smaller and smaller and smaller? So the sun on this graph of radius here on the horizontal axis and the escape velocity on the vertical axis in kilometers per second, that's the actual size of the sun there, and that's the actual escape velocity, 600 kilometers per second. But what if we were to take that sun, that mass of the sun, and simply put it into a smaller sphere? If we put it into a sphere that's only this size, then the escape velocity would go up. If we make it smaller, the escape velocity goes up again. Remember, mass divided by radius, we're not changing the mass, we're just putting it into a smaller container. So r is changing, but mass isn't. And so if we keep on doing that and say, what if we put the same mass in a smaller container? What if we put it in something that's only the size of the UK and a little bit smaller? Then the escape velocity is now 30,000 kilometers per second. If we put the sun into a sphere the size of a city, the escape velocity is now 100,000. And finally, what if we put all the mass of the sun into a sphere of radius 3 kilometers? Well, now we get an escape velocity which is 300,000 kilometers per second. In other words, it is the speed of light. So at that point, I don't know how we would achieve it, but if we could take all the mass of the sun and put it into a 3 kilometer radius sphere, the escape velocity would be the speed of light, and that would be what we define as the event horizon. In other words, if the mass was any more compressed than that, we wouldn't know what was going on inside that event horizon, that sphere of radius 3 kilometers, because nothing could get out. This event horizon would be defined at the so-called Schwarzschild radius of 3 kilometers. The Schwarzschild radius is the radius at which the event horizon is deemed to occur, if you like. So I don't know how we would do that. And of course, we've just said that if we compress the sun into a 3 kilometer sphere, we get a black hole. Just because we don't know how to do it doesn't mean it can't be done. In principle, we could do this with any object. It doesn't have to be a star. For instance, what if we start with a different mass and ask the same question? If we start with this mass, how small a sphere do we have to pack this mass into in order to get the escape velocity up to the speed of light? If we wanted to start with the mass of the Earth, we would have to compress all of the mass of the Earth into something about the size of a marble, a radius of a few centimeters. Then we would have a sufficiently high density that the escape velocity would be the speed of light. What if we was to start with an object with the mass of the Moon? Smaller mass, therefore it needs a smaller sphere to pack into in order to give us escape velocity of the speed of light. The Moon would have to be compressed until it was about the size of a grain of sand. Then it would be a black hole. If we take a much smaller mass, for instance, the mass of Mount Everest, I'm not quite sure what that is, but let's just guess the mass of Mount Everest, that would have to be compressed down to about the size of an atom, and then you would have a black hole. So again, technologically, we have no understanding of how you could possibly do that. Take Mount Everest or the Moon or the Earth and compress them down to these sizes. We have an understanding that it can happen for stars because they are large enough to have much stronger gravitational forces. But in principle, we can take any mass we like and we can imagine what would happen if we compress it down to these sorts of sizes. So that's how escape velocity works. Let's have a think about general relativity, and it's really glossing over the details, because you can reduce general relativity down to this if you want to ignore all of the horrible maths and the mind-bending stuff. This is one way of representing the results of general relativity, g equals 8 pi t. G is effectively telling us about the geometry of space-time, which we think of as being flat in the sense of undistorted in the absence of matter and energy, but the right-hand side of this equation is effectively how much matter and energy and momentum do you have in the system you're considering. So it is a geometric way of interpreting the idea that, if you want to describe it more prosaically, you can say the existence of matter and energy basically distorts space, or if you like, it tells space how to curve. And the curvature of space tells mass how to move. Now, that's a rather prosaic way of writing down Einstein's general relativity, and then you can start asking questions like, well, what on earth do you mean by space being curved? Isn't space just nothing? And of course, it's rather difficult because if we think about a two-dimensional plane, like a piece of paper, we can imagine what would happen to a two-dimensional plane if you distort it, if you curve it into a third dimension. Our brains are capable of understanding what we mean by a two-dimensional surface being distorted or curved into a third dimension. But when you start saying, well, what about if you were to curve 3 dimensions? Well, the only sort of way that makes any sense at all is if you say, well, it's actually curving into another dimension. But humans are not good at imagining these things because our brains are not wired that way. Our brains are the result of 1 million years or more than 1 million years of evolution. And basically, we survived because we figured out, is that a lion behind that bush going to eat me or not? And where does the next meal come from? Our minds are not hardwired to understand things like quantum mechanics and general relativity and curved space. So the mathematics tells us how to deal with this, and we can say, well, matter distorts space and time in the following way, and then when space and time distort, that tells us how matter behaves. That's one way that Einstein tried to tie everything together in his general theory of relativity. The maths is awful if you try and actually sit down and understand it all, but conceptually, that's what is actually happening. So we tend to try and visualize it. If we do attempt to visualize it, we often think in terms of, well, let's imagine space is a two-dimensional space, and then we can imagine a distortion. For instance, what if we put a very massive object in the middle of that two-dimensional space? We get this sort of familiar picture of a sort of a funnel. If we were to put a black hole in the middle of two-dimensional space, it would distort space so much it would produce basically an infinitely deep funnel. If it was only a finite mass that's placed in a position, such as the sun or the earth, it would produce a dip in this two-dimensional space. So that's not what is happening, but that's the way we try and visualize it, because that's the only way we can visualize it, because we cannot imagine what that would look like in three-dimensional space. So we resort to saying, let's imagine we're in a two-dimensional universe, and the existence of matter will put dips into this two-dimensional rubber sheet, and a black hole will produce an infinitely deep gravitational well in this two-dimensional sheet. And that's why whenever you see an artist's impression of a black hole, it always looks like a funnel, because you can't draw it any other way. You can't possibly draw the true three-dimensional distortion of space because it's curving into a fourth dimension, and no one can illustrate that. So we have to resort to saying, well, that's wrong, but it's as good as we're going to get because basically we just have too feeble imagination to actually visualize what's actually going on. That's, in a sense, the genius of Einstein is, although he attempted to visualize what was happening, he didn't worry about the fact that it's a tricky thing to imagine. He let the maths do the talking, and the maths told him that's how things are. Why do we believe him when he says, general relativity, this is great, this is my theory? Why did, in the beginning of the 1900s, so many people jump on general relativity and say, well, it's worth taking this general relativity to the extremes and asking what happens if a star collapses? What happens if a star gets compressed to a very small volume? Well, we believe general relativity because it's made various predictions which have turned out to be quite correct. For instance, the precession of the orbit of Mercury. When you look at the orbit of Mercury, it looks like it's going around the sun in an ellipse. Strictly speaking, it isn't an ellipse. It's not a closed loop. It changes ever so slightly. The distance of closest approach, the perihelion, actually moves slightly from year to year to year. Newton knew about this, and Newton's theories of gravitation were able to correct for most of the precession, based on the understanding of how objects move around the sun and other objects in the solar system. But there was still a tiny bit of that perihelion motion that was left that couldn't be explained by Newton. Along came Einstein. He applied general relativity to the problem, and lo and behold, it precisely predicted within the experimental errors the perihelion precession of Mercury. So the fact that Einstein was able to explain something that Newton couldn't was very good evidence that Newton is onto a good thing here. There are other pieces of evidence. For instance, if general relativity is right, then starlight, as it grazes the sun, shouldn't travel in a straight line. It should go in a slight bend because the sun is distorting space and time, and as a result, starlight, as it goes past the sun, is gravitationally bent or lensed as it passes. Again, this is not something that Newton didn't know about, but when you calculate using Newtonian mechanics what that bend of light should be, you don't get quite the right answer. It's been experimentally determined by measuring the positions of stars when the sun is not in that part of the sky, and then 6 months later, when the sun is close to these stars, of course the sun would be too bright to see the stars, so you wait until there's an eclipse to block out the sun and then check where those stars are. Now that the starlight is just grazing the surface of the sun, and you see how much they've shifted compared to 6 months ago when the sun wasn't anywhere near that particular patch of star-lit sky. And again, Newton can explain some of this curvature, but Einstein explained all of it. So we have some belief that Einstein was right. Now, most people can get their heads around the fact that, okay, maybe matter is having some effect on space, but it's really difficult to try and understand how matter affects time. So again, unless there's some experimental evidence, most people wouldn't have accepted this as one of the results of general relativity. But we now know special relativity and general relativity both say time is not as immutable as we first thought. If things move fast, time changes. If you have a large mass close by, time changes. And this has been experimentally verified a number of different times. It was originally verified, I think this was back in the 1970s, maybe the 60s. You can tell from the fashion, perhaps. Basically, you take a few atomic clocks, you put them on aircraft, you leave duplicates of the atomic clocks on the ground, and you fly the plane in different directions at the same speed and at different heights, in other words, at different gravitational fields. Different heights means different distance from the center of the Earth, so you're effectively producing general relativistic effects as well as special relativistic effects. And when that was done with these atomic clocks, the predictions of special relativity and general relativity were found to be basically dead on. So yes, time does slow down in the presence of a gravitational field, and as well as when objects are moving quickly. And it's just as well we do understand that, because without that, we would not be able to get the accuracy that we all take for granted in GPS satellites. GPS satellites are in orbit around the Earth. They're moving considerably in terms of speed relative to the rest of us. So special relativity has to be taken into account. But also they are further away from the ground than the rest of us on the surface of the Earth. And they could well be in slightly different heights. They are nominally at the same height, but there might be a slight height difference between different satellites, which means they will all have internally atomic clocks that are running at different speeds. If you don't take that into account and you just let these clocks drift, then you will get errors when you try and work out where is my ship, where is my car, by basically taking signals from the various satellites. It's the time delays from where you are to the satellites that determines where you are on Earth. And so you need the atomic clocks on these various satellites so that you know when the signal left to work out where you are on the surface of the Earth. All of the calculations that are done by the receiver must take into account small corrections due to relativity. If that wasn't the case, your GPS would not work accurately. So we have lots of evidence that Einstein was right. So we believe him. When he says mass changes space and time, when mass distorts space and slows time down, because of all the evidence we have, we basically believe him. One of the predictions of general relativity is gravitational waves. This was thought to be a rather interesting but of no relevance whatsoever discovery at the time. The idea that because matter can warp space, what if you have two things, for instance, two black holes orbiting around each other, or two black holes banging into each other? That will produce ripples in space and time, which will radiate like ripples in a pond. If you throw a stone into the middle of a pond, you'll get ripples radiating outwards. This is rather different from the ripples in the pond in the sense that if we think of a cylindrical object and we think of these so-called gravitational waves, these ripples in space and time moving through the cylinder, they will make the cylinder stretch, not in the longitudinal sense as the wave passes. Let's say the wave is passing from the right to the left here. The cross-section of this cylinder will distort into an ellipse one way, then an ellipse the other way, and then an ellipse one way, and an ellipse the other way. In other words, the height or the width of the ellipse will initially be longer one way, shorter the other, and then vice versa as the wave passes through. The prediction was these gravitational waves ought to pass through objects at the speed of light. But this was thought to be, well, it's a prediction of general relativity, but it's of no consequence whatsoever because the size of this distortion would be so small. Even if you get two black holes banging into each other, the size of this distortion is going to be tiny, not the 20% distortion that we can see in this animation. The distortion would be more like 1 part in 10 to the power 20 or 1 part in 10 to the power 21. It'll be 1% of 1 millionth of 1 millionth of 1 millionth. How on earth are you going to ever measure anything so small? So at the time it was considered to be, well, mathematically that's the prediction, but there's no way we'll ever experimentally verify that. I'll come back to that later. So now we look at the third piece of the jigsaw, stars and galaxies. So this rather weird artist's impression of what might a supernova look like, I think we have to take that with a pinch of salt. But yes, massive stars will go supernova at the end of their lives. Massive stars, they are so massive, gravity is going to be strong enough to actually crush the star. Once the thermonuclear reactions in the core of the star are no longer able to support the rest of the star will collapse. Whether it looks like this and whether the shockwave actually cuts a planet in half, well, we can just say a little bit of artistic license there. But we know huge amounts of energy are released in a supernova because of the gravitational collapse. Stars, for most of their lives, are a balance between gravity trying to crush them and thermonuclear reactions producing radiation pressure, which is balancing that gravity. But as soon as the fuel runs out, massive stars can undergo supernova explosions. Well, explosion isn't quite the right word, but you know what I mean. A supernova at the end of its life. And if it's massive enough, the core that's left is dense enough that it becomes a black hole. It might be a neutron star, but if the star is massive enough, it can produce a black hole. And a star passing too close to a black hole might have a really bad day. A black hole can basically shred a star if the star gets too close. So in this particular case, there was a black hole sitting there which we didn't notice, but as the star got a little bit too close, tidal effects, it's not necessarily the gravity, it's the difference in gravity, one point in space to another, can rip the star apart. And notice that the star that gets ripped apart doesn't simply get sucked down into the middle of a black hole immediately, in much the same way that when you empty a bathtub, the water doesn't go down the plug hole immediately. The water tends to circulate and the individual bits of water take their turn to go down the plug hole. Same sort of idea. All the material from the star ends up circulating in a large disk, a so-called accretion disk, and the inner parts of the disk are feeding into the black hole, and the outer parts of the disk are waiting their turn, slowly moving inwards, being consumed by the black hole. The amount of energy that's released, let me just run the animation again just because it's a nice animation. There's the black hole that we otherwise wouldn't see, but as the star gets too close, it gets ripped apart. Some material goes into the black hole, but most of it ends up circulating. The accretion disk gets hot simply because all of the matter is the friction between all of the matter in this region. Everything is rubbing against each other, waiting their turn to go into the black hole. And so the whole of the accretion disk gets hot. It can radiate in the visible, it can radiate in the UV, it can radiate in the radio and in the X-ray. And sometimes you might get these jets coming out. We don't really understand the nature of these jets. It's almost certainly related to the magnetic fields that are in the neighborhood. And as the material is slowly going into the black hole, some of the energy that's tied up in the accretion disk ends up getting ejected along, if you like, the north and south poles of the spinning object. But again, we don't really understand all of the details. It probably occurs on stellar mass black holes. It certainly occurs on larger black holes, the supermassive black holes at the centers of galaxies. So the idea of the tidal forces ripping apart anything that gets too close, this has often been popularized by saying if a person gets too close to a black hole, the gravity at your feet is much stronger than the gravity at your head, so you get stretched out, so-called spaghettification, otherwise known as the noodle effect. It does actually depend on how big the black hole is, because it does depend on the tidal forces. Rather counterintuitively, if the black hole is quite large, the tidal forces aren't as large as they would be for a smaller black hole. So whether or not you get spaghettified depends on what size black hole you are falling into. But we can actually see what's going on at the center of our galaxy. This was done quite a few years ago. By zooming into the center of the galaxy, a number of individual stars were seen, each of which appears to be orbiting in elliptical orbits around something we can't see. That circle there indicates the center, or at least the focus, of all of these various ellipses. So this star, for instance, something is taking a star and whipping it round. The timescales here are a few years. So something is taking a very large star and whipping it around, so there must be very strong gravitational forces in this particular point indicated by the circle, and yet nothing can be seen there. That's the center of our galaxy, implying that given that if we know Kepler's laws apply, or at least if we assume Kepler's laws apply, that something is orbiting a very massive object at the center of our galaxy, using Kepler's laws, we can simply work out what must the mass be in order that a star with this particular orbit ends up taking 10 years to go around this central object. If we do that, we find the supermassive black hole. From here on, I'll simply be using SMBH for supermassive black hole. We find that this particular supermassive black hole at the center of our galaxy must have a mass of about 4 million solar masses. So this symbol on the right-hand side here, capital M circle dot, that's just shorthand for the mass of our sun. There's nothing special about the mass of our sun. It's just a more convenient unit to use than kilograms or tons. It is 2 times 10 to the 30 kilograms. And to get an idea of how large this black hole is, let's just use the solar system as a sort of yardstick. So let's just dim that down so that we don't get confused by all of the details. If it's 4 million solar masses, remember, if it's a black hole, we can work out the size of the event horizon because this escape velocity depends only on mass divided by radius. So if we know the mass, we can work out the radius. And it turns out that the size of the black hole at the center of our galaxy is much, much smaller than the orbit of Mercury. So it is very much a tiny thing. Remember, the stars are orbiting around this object, but the object itself is much smaller than our solar system. It's not even close to being light years in size. It's not barely light hours in size. But there are other supermassive black holes that are much larger than the one in the center of our galaxy. We can see the stars relatively easy in the center of our galaxy. It's a little more tricky to see stars in other galaxies, but we can estimate the size of the supermassive black hole in other galaxies. For instance, in the Andromeda galaxy, the supermassive black hole is about 250 million solar masses. So there's the one in the center of our galaxy. In Andromeda, it would be about the size of the orbit of Jupiter, very much larger because of the larger mass. In the Sombrero galaxy, it's been estimated that the supermassive black hole has a mass of about 1 billion solar masses. So rather than just being the size of Jupiter's orbit, it would be the size of nearly Neptune's orbit. Absolutely huge. I'm not sure what the record is for the largest so far, but as of a little while ago, the largest one I could find was larger than 20 billion solar masses, and it's too large to fit on my diagram, so that's how large it would be. Absolutely huge compared to the size of our local solar system. And that's not, by no means necessarily the largest that can exist. We believe that when galaxies start merging with each other, the supermassive black holes at the centers of those galaxies will merge, and so there's no reason why supermassive black holes can't end up much, much bigger than only a few billion solar masses. Rather interestingly, relatively recently, it's been found by telescopes such as the Hubble Space Telescope and others, that if you look not only at the centers of galaxies do you see supermassive black holes, but actually, if you look at the center of star clusters, you see massive black holes. Now, that's a relatively recent discovery. So the question then is, well, we first saw supermassive black holes in galaxies, and now we think every galaxy has a supermassive black hole at its center. Have we been duped into thinking that star clusters are just clusters of stars? Is it possible that the center of large star clusters, again, have black holes at their heart? And are the black holes related to how the star clusters came to be in the first place? So this is a burgeoning area of research where people are starting to look at star clusters within our own galaxy, looking at them in a new light, if you'll excuse the pun, trying to figure out whether or not their dynamics are quite what we think they are, because of things that might well be lurking at the centers. So let's look at the fourth piece of the jigsaw, which is how we go about detecting gravity. And this has been revolutionized. There have been some space probes before this, but it's been revolutionized by LIGO, the interferometer, the Laser Interferometer Gravitational Observatory. There originally were 2 of them. There's more coming online all the time in Europe and elsewhere, India and Japan. But the original pair of detectors was one in Washington State and one in Louisiana, large L-shaped observatories. Why do you have 2 observatories? Well, you could say that's the way the American government always works. Why build one when you can spend twice as much money and build 2? No, it was done because nobody would believe the result unless you can actually prove that you get the same signal in 2 observatories 3,000 miles apart. If you're looking for something cosmic, it won't make a lot of difference 3,000 miles. But remember, you're looking for tiny variations. So let's just remind ourselves what it is we're actually doing here in this gravitational wave observatory. Each of these 2 L's is effectively a large laser here, which is split into 2, and the laser beams go down each of the 4-kilometer-long arms, bounce off a mirror at the end, and then come back again. And actually, they bounce backwards and forwards a few times, but let's ignore that for the moment. You can imagine the laser starts here, goes down each arm, and then comes back. If those two arms are exactly the same length, then those two laser beams will hit the mirrors at the end and come back and arrive at the same time. But remember what we said, that little animation of what would happen if a gravitational wave passes through a material, whether or not that material is a piece of the Earth or the gravitational wave observatory itself. Remember, it gets stretched one way and then compressed, stretched and then compressed. So if a gravitational wave passes through this observatory, then those two arms, one is going to be stretched ever so slightly while the other one is compressed, or shortened, and then vice versa. In other words, the light should take the same length of time to go down each arm and come back to the center. But if a gravitational wave passes through, then those arms get slightly longer, slightly shorter, slightly longer, slightly shorter. And so the laser light going down those two arms, one will arrive slightly early and then slightly late, and then slightly early and then slightly late. So there will be small variations in the timing of the laser light coming down these two arms. What's going on at the end? This is the actual mirror, or one of the sets of mirrors that are reflecting the laser light from the end of the arm back to the central laser complex. These mirrors are held in a sort of a pendulum. Remember, we're trying to measure very, very, very small changes in the length of these arms. So the last thing you want is for this mirror to be mounted solidly on the floor, and then the slightest vibration of the ground will make the mirror go backwards and forwards by maybe a fraction of a micron, but that's too much. Remember, we're trying to measure tiny, tiny distances. So it's set in a sort of a pendulum to try and isolate the mirror from any effects of people walking, cars going by, trains going by a few miles away, the rumble of an earthquake, etc. That's, again, another reason for having these two observatories 3,000 miles apart. Hopefully, anything that affects one won't affect the other. Whereas if you do genuinely see a gravitational wave pass through the Earth, both of them should register, in principle, the same event. But the amount of motion that we're talking about is going to be tiny. 1 part in 10 to the 20 is the effect that we might get from two black holes colliding with each other. So if you equate, well, how much does this mirror actually move over this 4-kilometer laser run from the original laser to the mirror, how much does this surface of the mirror move? It is way, way, way smaller than an atom. It's actually smaller than the nucleus of an atom. It's actually smaller than the proton inside the nucleus of an atom. It is tiny, tiny variation. So the engineering precision required for this observatory is absolutely phenomenal. When the two lasers eventually get back to the center of the observatory, it goes through a phenomenally complex interferometer to try and measure these tiny differences between the laser light going in one arm and the laser light coming back from the other arm. And what is truly, truly incredible is that it apparently works. Okay, a fair bit of money was thrown at this project, but I still find it difficult to believe that anybody put the money up for this project, because it sounds so crazy that you could ever expect it to work. We're going to send light down two arms, and we're going to measure the difference in the mirror positions to way smaller than the diameter of one proton. And yet they seem to succeed. Back in 2015, they produced these two traces, which at first sight look like just noise. But let's just separate them out. That was the signal seen at one of the observatories, and that was the signal seen at the other observatory. Notice that they have the same basic pattern. To start with, this is on a time scale, by the way, of just a fraction of a second. This is just a few tenths of a second here along the axis there. Essentially, nothing was seen, and then there appears to be the start of something oscillating. It seems to be going up and down and up and down, and it's going larger and larger amplitude and faster, and then it disappears. And what did you see in the other observatory? You see nothing much, and then there appears to be an up and a down, and the amplitude is increasing, and the frequency is increasing, and then it dies away again. And these were seen at not quite the same time. There was a fraction of a second difference, because at the speed of light, you would expect to have a slight difference of the arrival at one observatory compared to the arrival at the other observatory 3,000 miles away. but when you put them on top of each other, you realize that they are actually observing the same thing. So how do you go about interpreting this variation? And let me just remind you that this variation here, the strain, the amount that these lengths have changed compared to the original length. So it's delta L over L, the change in length compared to the original length. That's 1 part in 10 to the 21. And yet the noise levels were low enough to actually pick out these signals. What do the theorists make of this? The theorists can actually deduce a lot. They don't just say, oh, that's a noisy looking wiggle. The theorists say, well, looking at how the amplitude changes as a function of time, and looking at how the frequency changes as a function of time, and looking at how it dies away, we can come to the following conclusion. We conclude that what's actually happened is two black holes have merged with each other. A black hole of mass 29 solar masses has merged with another black hole of mass 36 solar masses. And it resulted in a combined black hole with a mass of 63 solar masses. Anybody good at maths knows that 29 plus 36 doesn't equal 63. 3 solar masses of matter no longer exist after this merger of these two black holes. They've merged together to produce a mass that's 3 solar masses less than the original. Where did those 3 solar masses go? Those 3 solar masses have been converted into gravitational waves. For a fraction of a second, the amount of energy coming out of this merger of 2 black holes was absolutely phenomenal. In a tenth of a second, 3 solar masses were released as energy. In about a tenth of a second, that's how long it took for 3 solar masses to be converted into gravitational waves and go spreading out into the universe. For that tenth of a second, the energy coming out of this one event was more than the total of energy coming out of all the stars in all of the galaxies in the observable universe. This one event was more energetic than the rest of the universe put together. So that is how energetic black holes can be when they decide to collide with each other. And that particular event was one of the most dramatic events, and it's no surprise that when you first build an instrument, the first thing you see is one of the most dramatic events, because by definition, your instrument hopefully will be getting better and better and allowing you to detect fainter and fainter or smaller and smaller black hole collisions, but the first one was an absolute monster. That's not the end of it, because having realized that in principle it works, you can actually build these to the right precision, and they're being built in America and in India and Japan and Europe and elsewhere. You can now start putting them together and saying, right, can we actually now see if we can correlate all of these and see the same thing across all of the world, rather than just in different parts of America. Not only that, but they're having ideas like, why should we be limited to 4 kilometers in the length of our arms for the laser bouncing off these mirrors? It would be great to see gravitational waves of different frequencies and different wavelengths, which means we would need different length arms in our interferometer. So there's now an idea called LISA, the Laser Interferometer Space Antenna, sometimes called ELISA, the Evolved Laser Interferometer Space Antenna. The idea is you put up satellites with lasers on board and you fire the laser between the satellites. You're not limited to just having an L. Why not have a triangle, and then you can bounce lasers backwards and forwards between them. And you don't need to have physical pipes going from one to the other, because the pipes on the LIGO interferometer on Earth were there so you could evacuate it to get the laser going backwards and forwards. Here, you're just using the vacuum of space. And there's no reason why you can't have 1,000,000 kilometers in between these 3 spacecraft. The idea of can you get spacecraft to fly in formation to the accuracy needed in order to do laser interferometry has already been tested. That particular demonstrator was done quite a few years ago, and it's been proved that we have the technology, the technological capability of building this thing. Funding is now being sought, and the intention is that sometime in the 2030s, this laser interferometer will be built into space. It'll be put into an Earth-trailing orbit, and then these 3 satellites will bounce lasers back off each other and be able to see things that LIGO simply wasn't able to see. And that's because LIGO is sensitive to a particular wavelength and a particular frequency of waves. It's determined by the length of the arms, the 4-kilometer arms. So it's very good at, for instance, looking at the merger of black holes or the merger of neutron stars, which is what LIGO has observed up till now. But if LISA or ELISA is ever built, then it will be sensitive not to systems colliding or systems merging on timescales of a fraction of a second. It will be sensitive to things happening on periods of seconds to minutes to hours, much longer wavelengths. So it won't necessarily be as sensitive to 2 small black holes banging into each other or orbiting each other, but it should be sensitive to much larger systems such as the supermassive black holes at the center of our galaxy or the center of other galaxies. It's thought maybe it would also be sensitive to other gravitational waves. What about the biggest gravitational wave you can actually imagine, the one that came from the Big Bang? Surely the Big Bang produced ripples in space-time. Is it possible to actually measure those by making a space interferometer large enough to be sensitive to the sort of ripples that we would expect from the Big Bang? Maybe so. If we want to actually see a black hole, that's rather tricky, but a little while ago, somebody had the bright idea of connecting together lots of radio telescopes across the world, putting them together in one large interferometer, so that you end up with effectively a radio dish approximately the size of the Earth. That gives you an enormous power in terms of resolution. It allows you to look at objects and see them in great detail. Obviously, you're not collecting many radio waves because 99.999% of the radio waves that arrive splash into the ocean rather than hit these dishes. But with these separations, you're able to get the resolution, if rather tricky to get the sensitivity. And that was used to image the accretion disk around M87. The M87 is the the brightest galaxy in the Virgo cluster, and it was known to have a supermassive black hole with a mass of about 6 billion solar masses, and that was imaged, and that's the accretion disk that they saw. You can't image the black hole itself. There's a sort of shadow in the middle because any light that's coming from the region of the black hole is going to be distorted by the extreme curvature of space produced by the black hole. But we do see the main parts of the accretion disk, and we see that the accretion disk isn't uniformly illuminated. This particular donut doesn't appear to be producing light uniformly everywhere, which is what you would expect if you've got an accretion disk where lots of objects are moving very quickly as they're waiting their turn to go into the black hole. This is what we think we're actually looking at. This is a simulation. Seen from above, the accretion disk just looks like a pancake. But seen from the side, it might be as thin as Saturn's rings, but remember, Saturn's rings disappear when you look at them edge on, but this accretion disk looks really weird when you look at it edge on. The front edge here looks quite thin, but what's going on up here and down there? That's simply the far part of the ring. If you imagine the ring is actually flat, that is the far side of the ring as seen from above, and that is the same part of the ring as seen from below. In other words, any light leaving the accretion disk on the other side has to get past the black hole in order to reach us. So any light coming from this part of the accretion disk effectively comes out and we can see it. Any light coming from the farthest part of the accretion disk has to pass the black hole, and there the space is very distorted, and that's why we get a shadow effect of not being able to see what's going on in this region, and getting this effect of, even if we're not looking at the accretion disk face on, we will still tend to get something that looks vaguely circular. And notice it's a little bit brighter on the left than it is on the right because of the nature of how these things circulate. If matter is circulating in the accretion disk, any matter that's traveling towards us will tend to look brighter than any matter traveling away from us. And that's why when we look at M87, we find bright splodges on one side rather than on the other. When we did the same thing by looking at what's going on in our own galaxy, Sagittarius A star, remember that's a supermassive black hole that's substantially smaller, only 4 million solar masses, not 6 billion solar masses, but we see a very similar structure. It's not the same. We have bright splodges in different places. It's a rather bigger challenge to image this, not because it's smaller, but simply because if it is smaller, the material is a lot closer to the black hole, so it'll be circulating faster, which means you can't simply take a nice long exposure to get as much data as possible, because that means all the detail that you would like to see gets smoothed out. With M87, it's such a monster black hole, the accretion disk will be orbiting very slowly, and so if you take an exposure that lasts all night, in other words, if you collect radio data all night, you can simply add it all together, because that particular system won't have changed much in 12 hours. Whereas it's thought that the black hole at the center of our galaxy will look different from 1 hour to the next, so they had to do much more careful processing of the data in order to pick out the sort of detail we see there. They're now hoping to go back and look at this, not quite as a video, but look at it at different times and actually see if they can see different parts of this structure changing. We have to remind ourselves that although the two systems are apparently the same size, in other words, the two diagrams I've shown, this one of Sagittarius and the previous one of M87, they look about the same size on the screen. That's because they look about the same size in the sky. Data has been taken and reprocessed recently to try and indicate, can we actually figure out what the magnetic fields are inside this accretion disk? Strictly speaking, that is not the actual magnetic field lines, but it gives you an idea of the modeling that tells us what we think is going on with the magnetic field inside the actual accretion disk itself. But just to make sure we understand that these are very different sizes, even though they appear the same size, when we actually put them in as the same scale, the actual size of the M87 accretion disk is very large. There's Pluto's orbit, so you can see the accretion disk of M87 is huge compared to our solar system. If Voyager was placed in that position, you'd see that Voyager hasn't even made it into the accretion disk if we place the accretion disk with its center where the sun is. If we compare that with what's going on in the Sagittarius A accretion disk, it's a tiny pixel there, and if we blow it up, we see that the entire accretion disk inside our galaxy is not even the size of Mercury's orbit. So although they look superficially similar, they are very different sizes. And this is keeping the theorists happy, because if you've got a black hole of billions of solar masses and a black hole of millions of solar masses, lo and behold, when accretion disks form, they look superficially very similar. So that's giving the theorists something to work on to try and understand, can they make sense of that particular observation. So we've been having a look at the definitions of escape velocity, the ideas of general relativity, a little think about stars and galaxies and the way massive stars produce stellar-sized black holes, and the fact that we have supermassive black holes at the center of galaxies. I'm not going to talk about evolution and how those supermassive black holes got to be there. That's something that James Webb is currently looking back in time to try and understand when those supermassive black holes actually formed. But it is still, I think, amazing that we can actually detect gravitational waves from black holes within, well, not simply black holes that are close by. I didn't mention the distance, but the LIGO result I was showing that showed the merger of two black holes, one of 29 solar masses, one of 36 solar masses. Those weren't in our galaxy. Those were in a galaxy 1.5 billion light years away, and yet we can still see the ripples in space-time over that enormous distance. I think credit needs to go to the scientists and the technicians and the engineers and the people doing the data analysis. The fact that these interferometers produce the sort of data that they do. We're almost taking it granted now that LIGO has been operating for quite a few years and is showing us all these black holes. But the engineering behind it is absolutely incredible. So we've had a look at science fact. Let's just spend a few minutes thinking about science fiction. I picked out 3 bits of Hollywood that represented something about black holes. The Disney's black hole, Ernest Borgnine, Maximilian Schell, and then the middle one, the Lost in Space reboot, and then on the right-hand side, the sci-fi horror Event Horizon. What's going on in each of these movies? Well, in one, a ship is parked right next to the Event Horizon. That doesn't seem to be a problem. They just went to the Event Horizon and parked and put the handbrake on, no problem. I'm not sure that was because they had some magical way of staying there, or whether, well, time slows down, so there's no problem in going to the Event Horizon and then basically just parking. In the middle one, what's happening? Just at the end of the film, as they're trying to escape from a planet, the ship is pulling away quite nicely from the planet, and then, for reasons we're not going to go into, the planet starts to form a black hole. The planet starts to collapse. Well, notwithstanding we don't know why that should happen, let's just assume the planet does collapse into a black hole. What happened to the ship was, as the planet collapsed into a black hole, the ship suddenly got pulled backwards because it was forming a black hole, and hence couldn't escape from the planet. In Event Horizon, there's a ship which is powered by an onboard black hole. I'll just give you a few seconds to think. Two of those films, the physics is very questionable or possibly non-existent. But for one of them, the physics is plausible. Which is it? I won't embarrass you by asking for a show of hands. In the black hole, sorry, let's just deal with the others first. In the black hole, no, you can't go and put the handbrake on the Event Horizon. Yes, time slows down. Yes, time stops at the Event Horizon. Time stops as seen by anybody else that's not in the black hole. In other words, if you were to watch somebody fall into a black hole, they would appear to freeze before they go into the black hole. But if you're on the ship, you just go plummeting in, because as far as you're concerned, time is going at the same speed it always does. It's always about relative time and the time as seen by someone else. So black hole, we're taking too many liberties. What about this one in the middle? That's a common misconception. There seems to be this idea that if you take matter and compress it into a black hole, suddenly that black hole becomes a lot stronger and gravitational pull increases. No, gravitational pull just depends on mass and distance. That's all. And so if you take a whole load of matter and compress it down to a point, the ship would not suddenly feel any greater pull. In much the same way that the Earth is going around the sun, if you were to take the sun and compress it into a black hole, the Earth would continue going around the sun. The gravitational pull would be exactly the same, because the same mass is pulling at the same distance. The fact that it's compressed is neither here nor there. Like we are being pulled to the center of the Earth, if you took the entire mass of the Earth and concentrated it in the middle of the Earth, we would feel exactly the same pull at this distance. So just because matter decides to become a black hole does not mean the ship suddenly feels 10 times more gravity and cannot escape the planet. So that's rubbish as well. But absolutely plausible is Event Horizon, the idea that you can use a black hole to power a starship, or at least a ship, whether it be inside the solar system or outside the solar system. It's only a hypothesis, but there's no rules of physics that say you can't do that. If you had a black hole with a mass of less than, let's say, a kilogram, you wouldn't have much energy available. If you've only got a kilogram of black hole, then there's, the maximum amount of energy you can get out of it is E equals mc squared. That's not much energy. But if you had a very large one, what if you had a black hole with a mass more than the mass of Mount Everest? Well, yes, and the hypothesis is that that black hole would radiate. Stephen Hawking hypothesized that there is such a thing as radiation from black holes. All black holes evaporate. We haven't been able to prove that yet, but most people think that Hawking was right. So black holes radiate energy from just outside the event horizon. Not from inside, because nothing can escape from inside, but just outside the event horizon, you can get Hawking radiation. But it's rather weak for large objects. It's stronger for smaller objects. So 1 kilogram is too small, Mount Everest is too large, but something in between, something fairly modest, let's say 1 million tons or so. If we start with a black hole with 1 million tons, the radiation output, the energy output from that black hole, would be something equivalent to 100 million nuclear power stations. And that amount of energy that would be available to you, how long would that last? That black hole would eventually evaporate, but only after about a century or so. So in principle, you could use a black hole with a mass of 1 million tons. You could use that to power your starship if you could harness the Hawking radiation coming off it. And you'd only need to replace that black hole once every 100 years by pulling into a refueling station, kicking out your little black hole and taking on a new one. How big would that black hole be? Well, 1 million tons would not be very large. A black hole that size, 1 million tons, we're talking something smaller than an atom. Remember, Mount Everest would be about the size of an atom, so only 1 million tons would be much, much smaller than an atom. So your engine room could be absolutely tiny, and it would last 100 years. And it gives you the equivalent of 100 million nuclear power stations, 100 million gigawatts of power available at your command. So we don't know how to do it, but that's only a technological problem. There's nothing wrong with the idea of using a black hole to power a starship across the solar system, or in principle, a starship. But what about the idea of, well, regardless of whether or not you're using it for propulsion, can you actually start distorting space and time in such a way that you can end up with a wormhole connecting two parts of space? Now, whether you call it a wormhole, whether you call it hyperspace, whether you call it something else, can you go from one part of space and then suddenly find yourself in another region of space because space has been so distorted? Well, it must be possible, because we've seen it so many times in Stargate and Contact and Star Wars and Interstellar and Star Trek. Yeah, we've seen it a zillion times. That's just because script writers get very bored spending lots of time people getting from A to B. So anything that's a shortcut is good for script writers. But if you can take a shortcut through space, remember we really should be talking about space-time as an entity, not space separate from time. So if you can take shortcuts through space, can you take shortcuts through time for the same principle? Can you find some combination of how to distribute matter and energy in such a way that you can end up with a wormhole that takes you back in time? Well, some of us think about time travel in terms of recent Hollywood movies, but for some of us, we have longer memories and we remember the time machine going back a bit further. And then there's the classics like Back to the Future and good old Doctor Who. Again, script writers love this because it gives you all sorts of things to play with. But the question is, does it break any laws of physics to think about changing space and time in such a way, don't know how to do it, but is it possible to change it in such a way that you end up with a shortcut back in time? Well, the answer is a definitive maybe. We're not too sure. Hawking didn't like this idea. He proposed the chronology protection conjecture. And as you would surmise, it's a conjecture. There's no proof, but he said, this doesn't sound right. There's nothing to stop you going back in time, but we know that if you go back in time, you can kill your grandfather, and then you end up with a paradox. So he suggested the chronology protection conjecture. Any wormhole that in principle allows time travel will collapse before anything has time to go through it and actually change history. So that's not proof. He's simply saying that's a way of making sure that you can't go back and kill your grandfather. He just said, making the universe safe for historians. But whenever we try and understand the universe, there is a problem. We know general relativity works exceedingly well. We've been testing it nearly to destruction for 100 years. We've tried everything to get it to break, and it apparently won't. General relativity seems to work in every circumstance in which we test it. And it's really good for really massive objects like stars and galaxies and black holes. And another theory, quantum mechanics or quantum theory, tells us about how things should behave on very small scales. Again, quantum mechanics has been around for 100 years. And again, we cannot break it. We've tested quantum mechanics over and over and over again. Quantum theory telling us how things should behave, atoms, molecules, any small objects that are smaller than a virus obey the rules of quantum mechanics. However, what if the object is very massive and very tiny? In principle, we need general relativity, which deals with massive objects, and we need quantum mechanics, which deals with small objects. So to understand black holes properly, which are massive and small, we need both of these things. We need general relativity, we need gravity, and we need quantum mechanics. So we need a theory of quantum gravity. And there's the problem. General relativity and quantum mechanics are not good bedfellows. Despite a lot of attempts, no one has been able to take general relativity and marry it up to quantum mechanics. Separately, they work really well. But if we want to understand black holes, we've got to get them together. A universal so-called theory of everything has proven to be rather elusive. Einstein was never convinced. He obviously believed in his general relativity. He was never convinced that quantum mechanics was the right description of the microscopic world. And he spent most of his later years wrestling with the theory of everything, which unfortunately turned a rather handsome young man like that into the Einstein that we all know and love. After many decades, he failed to get the theory of everything to work. If a genius like Einstein can't get his head around the problem of how to get gravity and quantum mechanics to work together so that we understand black holes, if Einstein couldn't do it, what is it going to take? Perhaps some unexpected discoveries from LIGO, from LISA, will point the way forward to a better understanding of black holes. We can but hope. Thank you all for listening.